Let's talk about parallax. Parallax is the phenomena that occurs when the position or perspective of an object appears to change depending on the viewer's vantage point or viewpoint. For the purposes of game development, we will be mainly using parallax scrolling, which is a technique commonly used in 2D games to create the illusion of depth in the background. If you can see it on the screen right now, in the first footage, the background scrolls statically. All the layers of the background, the clouds, the mountains, the trees, they're scrolling at the same rate. But if we implement parallax to this, the different layers of the background elements, such as the mountains, the trees, the buildings, they all scroll at a different rate, which gives off the effect of depth and makes the game world feel more dynamic and more immersive, which leads to better game experience. So this is a new series where we'll be starting off redeveloping the game, which I just published on the Play Store a couple of weeks back. We'll be starting from scratch, implementing all the functionalities, including the core game mechanics, even server-side stuff such as leaderboards, daily rewards, even a virtual shop where players can buy stuff. You can also implement in-app purchases, but I haven't thought about that yet, or nor have I implemented it yet. So that is something which you can maybe do in the future. Apart from that, in today's video, we'll mainly be concerned with player movement and implementing the actual parallax effect into the video. So we'll start off by creating a brand new project in Unity. So over here, I'm in the Unity hub. I'm going to choose 2D mobile core as the template. I'm going to name it Slime Tales YT, which is the name of my app, and YT is just short for YouTube. Later on, we're going to be downloading the universal rendering pipeline, which will be used for the 2D lighting, which will make the game look that much more better while we implement the lights. So let me just click on create project, and now we can start. While the uh, project is loading, we'll actually see the footage of parallax. In the first part, we can see the statically scrolling background, which we saw at the start of the video. But now we want the layers to move at independent rates. For example, the ground layers should move faster as compared to the background layer, which will give off a more dynamic feel and immersion effect when players play the game. So we'll wait for the project to load. Okay, right now we are in the a brand new scene. I changed the layers I changed the layout a little bit. This is what I feel more comfortable with. Now, to start off, we have a brand new scene which I've named game. This is where all of the core game logic is going to take place. Later on, when we implement player logins and player accounts, we'll create a new scene before this one. But to get started, we want to install the 2D PSD importer package, which is going to be necessary because all the images we are going to be using in this video I've created in Photoshop. So this package can be very useful for importing stuff from Photoshop. We have to go to package manager, Unity registry, and search the PSD importer package. Now this package comes by default with the 2D template which we had selected at the beginning, but in case you didn't know, you know how to install it now. Okay, now I've imported the two images we are going to be using today. The one is the player slime, which is the player character, and the other is the background image. A few changes which I've made to these sprites is for the player sprite, I have changed the pixels per unit to 1250, and for the background image, I've changed it from the mesh type from tight to full rect, because I found that the tight mesh type gives off some unwanted artifacts, which makes the image look kind of undesirable, to be very honest. So full rect. And as you can see in the video, for the player, I've changed the pixels per unit because the image is quite large. So increasing the pixels per unit will shrink the image when it appears on the game view or the actual screen. So now then I just clicked on apply and applied all the changes. The next thing which we want to do is import the Cinemachine package, because the Cinemachine is a camera package which Unity provides, which gives us access to a much more robust camera, which will automatically follow the player and all. So you can just search for Cinemachine in the package manager and install it. So We'll wait for that to install. Okay, now that this is installed, we can just close up the window, go to our hierarchy, and we can create a new empty game object. We'll call it cameras, and we'll store all the cameras in the scene inside this game object. We'll reset the transform, make the main camera the child of this game object, and then we'll create a new game object which will be the virtual camera. We'll just go to Cinemachine and click on a 2D camera, and I'll just name it VCam because it's going to be a virtual camera. Okay. Now, a few things to note. This camera needs something to follow, a target, which is going to be the player. So here I'm creating a new game object. I'll call it player. I'm going to reset the transform because we want it to appear in the center. And now I'm going to create a child of this game object. I'm going to call it as body because this is the way I like to do things in the scene hierarchy. For the player, I'll make a game object which will be a child. I'll name it body. For another feature, for example, if we want the player to have a trail, I'll name another game object trail, we make it the child of the player, and so on. Now inside the body, we're going to add sprite renderer as a component. This will just help us in displaying the sprites onto the screen. So I'll just drag the player sprite into the sprite renderer, and I'll just make the depth 35 so that it appears on the screen. Next thing, we want to drag the player game object into the follow component of the Cinemachine camera, and this will help us in camera tracking. Whenever the player moves, the camera will follow the player so that it never goes off screen. A few more things we want to change. We want to change the camera distance to 35 because we set the player's Z value to 35 and the lens ortho size to 20.25, which will make the player at a reasonable distance so that we can view the entire player without any of the other objects interfering with the sight. Okay, the next thing we want to do is set up the background. We have already set up the player. Now the only thing left to do is the background. Let me just set the Z value again to 35 so that it appears on the screen. Now, we want the background to be in such a way that it is completely visible on the screen. If you're using this image, you can just follow my values. I've found these out through trial and error, or you can use your own. And yeah, that is now the background is looking much nicer. And now all that's left to do is implement the actual parallax effect. Okay, so what we want to do is we want to make sure each layer moves at a different rate. And yeah, but no, okay, one more thing. The player is actually not visible. We want the player to be on top of the background. So one quick way to fix that is assign each layer a sorting group and give each of the sorting groups its own sorting layer. What I'm going to do is add component and just add the sorting group component. And now I'm going to add a new layer for each of the layers in our actual background. So one for the background far and so on. Okay, now that this is done, for the player, what I'm going to do is not assign it a new layer or a sorting layer. I'm just going to assign it on the same layer which the player is going to interact with, which in this case is the ground layer. One more thing to keep in mind, we want the player to be on top of everything in the ground layer. So the order in layer for the player is going to be something really, really high, something like I guess 50 or 100. In this case, I'm going to place the value at 100 maybe. Yeah, so that is it for the sorting layers. Now the player is actually visible on top of the background. Now the next thing we want to do is actually implement the parallax. Now we want to actually implement the parallax effect, but before that, the parallax will only occur when the player character moves, because the ground will only appear to move backwards when the player character moves forward. So for that, we want to actually implement a player controller script which will control the player movement. So I'm going to create a new folder. I'm going to name it scripts, and inside that new folder, I'm going to create a new C# script, and I'm going to call it as player controller. Right now, this script will only contain logic for the player to move horizontally, but later on, as we build up these videos and they pile up, we are going to be modifying the script in each video so that it handles all the logic for the player. For example, the jumping, the dashing, the collisions, and everything in between. So now we're in the player controller script. It's a normal mono behavior, a C# script. We want to get rid of all the starter code, boilerplate code, if you will. Now we want two variables, one for the speed and the other for something I like to call smooth. The way we are going to be implementing movement for the player is through a vector, through a function, my bad, through a function called vector3.lerp. And that function requires this, which we, as we will see later on. So the first private int speed and the other is going to be private int or float smooth. And I want both of these variables to be accessible to the Unity inspector or the Unity editor. So I'm going to be adding a serialized field attribute to both of these variables, and the underscore in front of these variables is just a naming convention I like to do. So I'm going to add serialized field to both of these variables now, so that they are edited, so that they can be edited in the Unity inspector. Okay, the next thing we want to do is actually call the update function, which is going to, which in itself is going to call the move function, which will handle all the logic for the player movement. Now we can go ahead and create this move function for the player. It's going to be a void, a private void move, and inside this function, the way we're going to be handling movement is we'll have a variable called target position. We will update this variable inside the move function and then set this variable inside the vector3.love function I mentioned earlier. So we can go ahead and create a new vector3. We'll call it target position, and we don't need to modify this variable inside the Unity inspector. So this won't have the serialized field attribute, which is actually a quick pro tip. The serialized field attribute, you don't have to make all the members public. You can just add a serialized field attribute and you can edit it in the Unity inspector. Okay, how are we going to update the target position variable? Okay, before that we have to actually, okay, before that we have to call the start function, and inside the start function we are going to assign or initialize the target position variable to the current position of the player. How do we get access to the current position of the player? Transform dot position, which is a attribute that Unity gives us right off the bat. Okay, now that this is all set up, we can go back to the move function, update the target position. So we're going to do target position dot x, because we only want reference to the horizontal axis of the player. Target position dot x plus equals. We're doing plus equals because we're going to be adding the speed into time dot delta time to the position of the player. So time dot delta time is basically just the time between each frame of the game, and we multiply it by time dot delta time because we want to make the movement of the player frame independent. So what happens is the lower end devices will have a lower frame rate, the higher end devices will have a higher frame rate. So if we make it dependent on the frame rate, some devices will make the player move faster, some will make the player move slower, and it will cause inconsistencies and undesirable behavior. So to make it frame rate independent and avoid all of these issues, we multiply by time dot delta time. So the way I like to think of it is, in physics we have a formula: speed is equal to distance upon time, and the distance is actually equal to speed into time. So I visualize it as something like speed into time, and the time is the time dot delta time. Okay, now we want to actually update the position of the player. And the way we're going to be do that is we're going to be updating the transform.position attribute of the player. And we're going to use the function I mentioned earlier, vector3.lerp. And inside this function, it takes three values. One, first is the initial position, which is the transform.position of the player. Next is the target position, which we have just updated in the move function. So we put that in. And third is the interpolation value between the 2 points. So this we will define by smooth into time dot delta time. So using smooth, we can control or check how fast we want the values to interpolate from transform dot position to target dot position. So what I mean by that is, in each frame we can control how fast the player moves using the smooth value. Now we can go back to the Unity editor. Hopefully there are no errors while the scripts are compiling. Okay, it is error free. And now we can just attach the player controller script to the player game object and set the values for speed and smooth. I want both of them to be 5. So I'm going to set that there. And now we can play the game and check if everything is working as it should. And it is. The player is moving in a horizontal direction without any jittering or whatsoever. But now we encounter another issue. One is that the background moves statically because we haven't implemented the parallax yet. And after a while, once the image runs out, we come up with a blue screen, which is unwanted behavior. And the next step is to fix this behavior. What we left to do is implement parallax finally. Now, there are two ways to implement parallax in any game scene. One is to camera. If we go to the main camera, we can see that the projection is orthographic. Orthographic is like 2D projection, so the depth value has no effect on the camera display. If we set it to perspective, then we don't have to actually code anything. The camera itself will manage the parallax for us, because it will behave like an actual 3D camera, or rather a real life camera. So the objects which are closer to the camera's Z value will appear to be moving faster, and the ones which are further away will appear to be moving slower. So in that case, we won't have to do anything coding related. But what I found is, for because this is a mobile game and it is going to target lower end devices, that will cause a lot of performance issues. Because let's take this for example, the clouds layer. It's going, if we set the z value for the clouds layer to be very far, something like 200, it will appear very small, and because of that we'll have to scale the game object, and scaling causes a lot of performance issues. The frame rate is barely, not even 30, I think something like 10 or 15 in very lower end mobile devices. And that is not something we want, because this is an endless runner game which should be across all devices, playable across all devices smoothly. The other way is through script. We will attach a script to each individual layer in the scene and control the movement speed through the script. So now we'll create a new script for the parallax, and over here we are inside the parallax script. Now to run the script, we need three main variables. Okay, so the three things we're going to be needing a variable for is, first of all, the camera position, so that we can keep a track or a reference to the position of the camera during each point of the update script. The second is the how fast we want each individual layer to move. So we can control that through a very simple float variable. We'll name it something like a parallax effect. And the third, which is kind of important but not really, is an offset. We encountered the issue where the background was moving past the screen and a blue screen was appearing. So we want the background to update its position when it knows that it has moved past the camera screen. So we need an offset for the length of each individual layer. In my case, it is something like 61.3. I have made the image in Photoshop, so I know. If you're using your own image, you need to figure it out. So yeah, these are the three variables which we need, and we do want to change them in the Unity inspector. So we are going to be attaching the serialized field attribute to each of these variables. So let me just set up the final variable. F is just for float. Okay, the next three things we need are again variables which we don't want to update in the Unity inspector, but we are still going to be needing a reference. First is the initial position of the layer, so that we can update this variable each time the layer moves past a certain point. The next is the cam position, so that we can have a temporary variable which we can keep on updating for calculations. And the third is a parallax effect, or the parallax variable, which will store the actual position, or the position of the layer if it was in its parallax state. More into that later on, but these are all the variables which we're going to be needing in this script. Yeah, we have cam position and parallax as floats and not vector threes, because we are only concerned with the horizontal direction and not all the three directions. So keeping that in mind, these are floats. Next is the start function, the standard Unity function. In this, we are only initializing the initial position, which is the transformed position, and the cam position, which we will get by the vcam variable we have defined. Here I am making a small error. Props if you can figure it out, but I will fix it later on in the video. And yeah, So the next thing left to do is implement the update function. The update function will handle all the logic for the parallax script, and it is the most important function. So let's implement it right now. So inside the update function, first of all, we want to update the cam position, and the cam position is going to be updated by multiplying the parallax effect by the actual camera position in the x-axis. So we are subtracting the parallax effect from 1 because we want the position of the lower end of the camera display, or the left point. And yeah, the next thing we want is the parallax value. In this case, we want the actual parallax value, so we directly multiply the cam position by the parallax effect, as you will see in the next line. Uh, yeah, here again I'm making a small, okay, I fixed the error now. The vcam variable is a transform in itself, so we don't need to specify the transform dot position, just the position dot x is fine. The next thing, we want to update the parallax value. We can do that by just simply multiplying the parallax effect value by the cam position dot x value. And yeah, that is it for these two. The next thing we want to do is actually update the position of the layer in the display. So how are we going to do that? Okay, yeah, one more error I'm fixing, which will soon turn out to be okay, never mind. Yeah, transform dot position. We want to update transform dot position. How are we going to update that? We are going to declare a new vector3, and the new keyword is used in Unity or C sharp. The first value is going to be initial position dot x plus the parallax, because we only want the parallax in the x direction. Then initial position dot y and initial position dot z are unchanged, they remain the same, because we are only concerned with horizontal parallax, not vertical parallax. I was thinking of implementing vertical parallax when the player jumps, but it was causing some issues with the vcam. The player was going off screen and below screen, some stupid stuff like that. Now, the next check we want to implement is to check if the layer is moving past the screen. The way we do that is we set a condition, an if condition, and check if the offset which we have defined at the beginning plus the initial position is greater than the cam position. If that condition is true, then what do we want to do? We just want to update the initial position to the offset plus the initial position, because the offset is the length of the layer. If we keep adding the offset every time the layer moves past the screen, then it will keep on moving forward as the player moves forward, and it will prevent the blue screen from appearing time and time again every time the player moves forward. So I have implemented the if condition, and now I'm just updating the initial position to the offset. I'm just adding the offset to the initial position dot x, not the entire initial position variable, because we only want the x attribute. So okay, now we can go back to the editor, wait for all the scripts to compile, and unfortunately we do have an error in line number 23. What is the error? Campus. Okay, yeah, this is the error I mentioned earlier. All we have to do is update the vcam.position to vcam.position.x, because we only want the x position and we are applying it to a float variable. Okay, so now we have the error-free code, and all we have to do is apply the parallax script to each of these layers. I'll just go on add component and add the parallax script. Now the offset is already set for us. The parallax effect. Okay. Now we, first of all, with zero parallax effect, this is how the game will run. It will keep on running just like it was. And once the screen moves past the, okay, never mind, we'll see that later, I guess. Okay, now that we have seen it without the parallax. Okay, we are fixing the error. We have dragged and dropped the vcam component to the parallax script. I guess I had forgotten to do that. Okay, now if we run the game, it is going to appear the same as before, But once the layer moves past the screen, after a while it will pop up again. Yeah, like we see now. The reason why this is happening is if we go into the scene view of the game and we observe over here, so the layer can't actually keep up with the speed of the player. It thinks that the screen it hasn't moved past the display, but actually it has. So one quick easy workaround is we make a child of the layer. We uh, we set it to the child and we move it forward by the offset which we have defined in the parallax script, which is 61.3 in my case. So now what we have essentially is an extended version of each layer. So before it moves past the screen, it is already getting updated, and now we don't have to worry about the layer not being able to keep up with the speed of the player. Now imagine if we don't do this and the speed of the player is in 5 something like 50. In that case the screen will never be able to be able to catch up with the player. So this is the best way to do this. And okay, yeah, here I am removing the parallax script from the child game objects. We don't want the child game objects to have the parallax script because we don't want them to update with the player. We just want them to update with the parent game objects. Now if we run it, there will be no blue screen, but still since the parallax is 0, it is still moving statically. But we have fixed one issue, which is the blue screen issue, which I like to call. Okay, so everything is working perfectly. Now we just have to update the values in the script for the parallax to actually get the parallax effect. Okay, so even in the scene view, we can see that there are no issues. Just before the screen moves past the layer, it gets updated, and now we just have to update the parallax effect values. So the background far layer should barely move, and it's going to have the highest value 0.99. You can modify these values through trial and error or through actually visualizing it. But here this is just an example. I'll just cut to when I have the actual values, and then you can see. So we'll just wait for inputting all these values and point. Okay, the foreground layer has no parallax. Okay, now I am back, and these are the new values for the parallax effect, 0 0.3, 0 0.7, 0.9 and 0.99. Now if we run the game, we can see a beautiful parallax effect. The foreground layer is moving faster, the ground layer is moving comparatively slower, and the background layer, the cloud layer rather, is barely moving at all. And this is the kind of effect we wanted in the very beginning. Now once more, if we go back to the parallax script and set all the values to 0 and we observe the static background, now you'll actually see how good the parallax was looking. Here it's not the same. All the layers are moving simultaneously. It's such a low quality game. That's what this looks like. But once we implement the actual parallax, then the game actually feels, it reeks of high quality. So this was all for today's video, guys. In the next video we'll be talking about lighting, and I'll see you guys in the next one. Peace.